Good day, my name is James Boylo and I'm going to be presenting my design project, which is a ball on plate system. Firstly, why I chose to do a ball on plate system. I work in the automation industry and PID loops are part of our projects that we use every single day. Now the problem with PID loops is that they're very hard to test inside a lab environment. So I'm using the ball and plate system as an analogy for real world systems, and the ball and plate system works very well in the sense that it has some very important features that we need in a PID control loop system. Namely, it's got a boundary condition where in real world systems such as a pipeline there are absolute limits in the actual system itself. So in a pipeline we've got pressure limits that if we go above a certain pressure we might start having failures inside of our components. So the ball and plate system represents this by the edges of the actual plate, where if the ball falls off the plate we've passed the boundary condition and we've exceeded the limits of the system. One other thing that's good about the ball and plate system as well is that it's open loop unstable, whereby if we aren't giving any control feedback to the system and the plate stops, the ball will roll off and fall off the plate. So there's a constant state of feedback and control to keep that ball near our set point. Okay, so in my initial design phase, what I had to do, I had to first make a block diagram of the ball and plate system. This was just the basic components that I was going to use for the system. I decided to use Arduino microcontroller because it's readily available, it's cheap, and it has the processing power that my system requires. I decided to use two servo motors to control the position of the X and the Y axis, because the servo motors they've got the required torque, because the ball itself is actually quite heavy. We've got a 65 Newton ball that we have to move. So that's why I used the servo motors. Also, it's very easily controlled by the Arduino using pulse width modulation to actually set our angle. Now the servo motors itself have got a 180-degree arc radius, so we can go plus 90 and minus 90 for our position control. And then for my interface, I decided to use a 16:2 LCD screen, which will basically just ask the user which type of function they want to use, and it will tell you when the unit is running. I've also got a few buttons that will select the different functions, and we're going to use that through one analog input. Now our design specifications for this, we want to limit the overshoot that we achieve, because obviously when we are giving a set point to the ball, we can't overshoot that set point by too much, because we go back to the real world analogy of the system, like with an oven. If we got a set point of 400 degrees, we might actually start damaging components if we overshoot that 400 by too much. So if we overshoot to about 500 degrees, maybe we start burning bread, or we start going past the specification of the heating elements. So that's one of the main design specifications, is to limit that overshoot. The next thing that we want to do in a PID system, we want to have a very fast settling time. So how the PID works, we actually introduce an error and we overshoot that error, and then we come back and we reduce that amount of error, and we do this in stages until we get within our set point range. Now we don't want our settling time to be too long, because then the system is just going to take too long to get there. So we want to reduce that settling time to about 2 seconds. Another thing that we want to introduce into our design is to reduce noise and jitter. So when the system is at a set point, we don't want to be correcting too much too often, because that's just going to reduce the life span of all the components within the system. And then the final thing that we want to do is we want to be able to handle outside disturbances. So when we're in a control loop, like in a circle function, and there's a big outside disturbance that throws it off. We want our program to be able to recognize that, correct it, put it on the correct path, and carry on. We don't want the disturbance to be able to stop the whole system from working. Now, after our initial block diagram, we had to do the mechanical design. So I used Inventor to do an initial CAD model of the system. Once I had the CAD model, I built it, and these ball and plate designs have been done before, so I want to do an improvement on previous designs. And one of the areas that I focused on was actually the joint from the servo to the plate. Now, most systems like this use a universal joint to achieve this. I decided to go with a magnetic ball joint, firstly because of the low coefficient of friction between the ball and the bushing, which allows for a very smooth operation, and also the amount of freedom of movement I have around on the magnetic ball joint, which allows for a very accurate system. And also with the magnetic ball joint, there's no backlash, where in a universal joint you have to spend a lot of money for a high quality component to get to that zero backlash figure. Now, once I designed the actual and built my first iteration of my prototype, one of the things that started to affect the system was the rotation around the Z-axis, because I had only one control arm from the servo. So that's one of the improvements that I had to do over my first prototype, was make a dual upright system to reduce that twisting. Now, that twisting is very important because we assume when we in the control system that when we do a correction in the X or Y axis, that only the X or Y axis moves. Now, with that rotation around the Z axis, we start to have like this infinite loop where you're trying to correct on your Z and you're introducing an error on your Y axis. So it was very important that I got rid of that in the initial stages. Next thing I had to do was develop the software design. So first thing that we had to do, obviously with the screen, we had to be able to select the different positioning functions. So I decided to go with a centering function, a circle function, an ellipse function, and an infinity function to show how that I actually have control over the ball in all the different aspects on the plate. The next thing that we had to do is we had to sense if the ball was on the plate. So if the ball is not present, we're going back to we don't want to have it jittering around, and because there is always noise in the electrical signals. So if the ball's not on the plate, this plate will be jittering back and forth, which obviously reduces the lifespan of all the components. So one easy way to get rid of that is to sense if the ball is on the plate or not. So if it's not on the plate, we're actually not even sending signals to the servo motors. Next thing how we do that as well, we're attaching and detaching the servo motors. So only when we want to move, when we've sensed that the ball is on the plate, that's only when we attach our servo motors and start sending those pulse width modulated signals to the servos for the positioning control. Next thing in the program, I got variation limiting. What that is, I'm actually comparing my XY position that I obtained to the previous XY position, and I've set in a limit of 20% maximum variation. So if I get a bad signal, which is very different from my previous reading, my program actually ignores that and it rereads the XY position, and it's constantly searching for nothing more than a 20% variation. Now, one effect that it has on the system, it reduces the speed of my system, but it increases the accuracy, which is a trade-off I was willing to make. And then obviously the last thing that I needed to implement was a software filter in the software, and all that does is it's an averaging function. So I'm actually I'm getting the XY coordinates 4 times before I accept that as a measurement. And basically what that does, it reduces noise, because noise is completely random, and when something's completely random, we can assume that the amount above and below our set point that noise occurs, if we average it out, it actually gives us a very accurate representation of where the ball is. Okay, after my software design, I had to do my circuit design for my breakout board. So this is just in Eagle CAD, and it just allows for all my component values, and just makes for easy reading of the circuit and allows for fault finding of the circuit. And then finally, once the whole thing was done, we had to do performance analysis. So as you can see on the graph here, we've got our X set point and our Y set point in green and blue. Now these waveforms are sine waveforms for the circle function, and then our feedback is the yellow and the red. And as you can see, like on the red, we've got a very good response time. So as the blue is increasing, our red is also increasing, and as it crosses over here, this is what we determine as our overshoot, because that's supposed to be our limit, and that's actually where we started to turn back. And that overshoot is within the limits we set ourselves of 10%. So it's actually a very good performing PID loop, because it's following the sine function pretty closely. We can see a little bit of sparks in the actual program, and this would be seen as jitter in the table, but there's not many at all. So we know that all our filtering and noise reduction functions are working well. Now we can have a look at the actual model itself working. So I'm going to turn it on. The screen will come on. We'll say that it's the ball and plate system by James Lowe, and then it will ask us to select a function. So we've got 4 functions we can select. We can center the ball, we can do an infinity symbol, we can do an ellipse, or we can do a circle. We're going to start off by centering the ball. So once we've selected the function, we can take the ball, we can put it on the system, and the system will center that ball for us. Then we can change the function to an infinity symbol, and this will plot out the actual track. Now as you can see, the ball is doing micro corrections, but this is going to be very close to what the function set points are. So we've got very little overshoot of the ball itself. We can change the function on the fly. We can do an ellipse. So there we go. Now we've got an ellipse. And you can see that the servos are doing very small micro corrections, which is great for accuracy. See that is just a little bit of noise in the plate, but there's not a lot. And then finally we can do a circle function. And then now we have to test our outside disturbances. So what happens when I do something like this? See, it will recognize that, it will correct, and it will put it back on the correct function. We can do that again, and it'll go back to the correct function. Now the last thing that we can do is we can center the ball, and then actually when the ball is centered, I disconnect the servos, and now you can see that there's no more jitter because I've got my set point. The program has determined that it's not there's no variation from the set point after a given number of cycles, and I've determined that to be 50 cycles. And then I actually disconnect the servos, so I've got no more feedback control, and the ball is set in the correct position. And to get it going again, we can reset. It will boot up. Now it's ready to go again, and it's going back on a circle function. Thank you very much.